The title of the Bitcoin white paper is Bitcoin, a peer-to-peer electronic cash system. What peer-to-peer is actually referring to in this paper is the notion that the users of Bitcoin will actually send transactions literally peer-to-peer, exactly like electronic cash. So in the same way that you go to a merchant in the real world and you literally hand cash to the merchant, you're going to be doing the same thing with Bitcoin transactions, because a transaction is digital cash. The peer-to-peer network being referred to in the title of the white paper is actually not the peer-to-peer network of the miners. The miners have a different peer-to-peer network. So there are two different peer-to-peer networks. There's the peer-to-peer network of the miners, which is a small world graph. Every miner is connected to every other miner. The reason why the miners connect to every other miner is because they want the other miners to be able to build on their block as quickly as possible. So when they find a block, they send it. Okay? So every miner is connected to every other miner. The users form a completely different peer-to-peer network. Okay? There's a bit of overlap, but you can consider to first order, it's just basically completely different. The users do not form a small world graph. The users are not literally all connected to one another. The users connect to other people that they care about. So when you transact with someone, you're connected with the person that you're sending a transaction to or receiving a transaction from. And so the users actually form a mesh network. It's a completely different network. Now there's some overlap because of course miners are also users, but it is not the case that users are miners. Okay? So there are really two different peer-to-peer networks. And the notion of peer-to-peer in the white paper is referring to the user one, where the users actually send transactions peer-to-peer. So also described in the original white paper is a notion called simplified payment verification. We have this literally in the white paper, and it to this day has actually never been fully implemented. And I want to say at the outset of this, I understood a lot of this stuff partially sort of over the years, because I've been involved in Bitcoin for a very long time. So I've been able to, sort of understood this early on in a partial way, but didn't understand it in a complete way until within the past, let's say about 1 year, particularly thanks to Craig Wright going out there saying some of these things over and over again, and me reflecting on it and thinking about it and gradually arriving at an understanding. So this knowledge is actually being reflected from Craig Wright. So I'll link to one of his articles on this, and you can read more information. But you can also just go back to the white paper. But the white paper doesn't explain some of the ways people have misunderstood it over time. So while the white paper is correct, it doesn't explain it in expansive detail, and so you may not understand it in a complete way. This matters for things like the way that SPV works right now for Bitcoin Core is basically just deeply broken. They rely on this notion of something called BIP37 Bloom filters, which the whole thing is just completely broken by design, is totally unscalable. It relies on the idea that the SPV wallets can basically confirm their transactions by using a Bloom filter hosted by a node. The problem with these Bloom filters is that they're ridiculously unscalable. They have to scan the entire blockchain to produce a new Bloom filter. And so it's extremely computationally intense and only works for small blocks and will just break massively for big blocks. Even if the nodes started charging money for stuff like this, they're not going to do it because it's just terribly, terribly unscalable. So we're going to do something completely different instead, which is probably what should happen is we need to set up a system whereby nodes can produce Merkel proofs and share those. Okay, so what I want to do next is, that's just a bit of background information. I want to explain a little bit about what SPV is and why it matters. So let's actually start with why it matters. I think that the most important reason why SPV matters is actually basically to allow the user to actually have digital cash and send it peer-to-peer in a way that works and scales. That SPV is something that you can have an SPV wallet that works right now. Well, it actually can't work right now. We get to this later, but you literally cannot do this right now because we don't have the APIs. So in order to do this right now, we have to start working on it, and it will take a year or two to finish building all of the APIs and have genuine SPV wallets. But in any case, if you were to have an SPV wallet, as soon as we roll out all of the APIs that makes this possible, it would keep working forever. Because even as the network scales to 100 transactions per second, 1,000 transactions per second, 10,000 transactions per second, 1,000,000 transactions per second, the SPV wallet does not care, and your current device is going to be just fine indefinitely into the future handling this because you don't have to handle the world's transactions on your consumer device. So it's going to scale. That's the most important reason. And it's genuinely sort of non-custodial and trust minimized. So it's really digital cash. It really allows you to possess digital cash and therefore have all the properties of cash legally. So things like, whatever limits in your local jurisdiction for cash transfers and things like this apply, because it is cash. And you can use cash. You can go to a merchant and deliver a cash. And this allows you to do things like offline payments. Okay, so the way SPV works is as follows. So built into the original design of Bitcoin is, so you have a block that contains transactions. So a block, you can think of as being, there's a block header, and then there's a giant list of transactions. Now, the block header has some information in there. It has something called the Merkel Route, okay? So the Merkel Route is actually, let's draw this out as it's a hash. And the Merkel Route is covered by the hash of the entire block, because the whole block itself is actually hashed. And so the Merkel root is sort of inside of the hash of the block. So basically, if you have a block, you can know what the Merkel root is. And if you have a block header, you can know things like, okay, well, you can know the block hash from the block header, and then you can confirm that the Merkel root is indeed inside of the block header. What the Merkel root has is basically a clever way of encoding every single transaction in the block in a way that you can prove that the transaction was contained inside of the block. So we have the root of the Merkel tree, and the Merkel tree is actually a binary tree. So I'm going to draw a triangle that encapsulates the tree, and what it really is you have at the top here a Merkel root, and then underneath that you've got 1, 2 other hashes underneath. So the Merkel root is actually the hash of 2 other hashes underneath. And then each one of these, let's go over this one first, is actually the hash of 2 more hashes. So if you understand what I'm drawing, boom, let's do another one, 2 more. It's a binary tree. So it's, you can draw the path from the Merkel root down, 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 all the way down to ultimately the hash of a transaction and a transaction itself. So what this means is, you have a way to know that a transaction is contained inside of a block, because what you need is you need the block header, you need the Merkel root, and then you need every single hash that goes down the tree all the way down to wherever your transaction is, including the transaction itself. And you need basically pairwise hashes all the way back up the tree. But you don't need the entire tree, and you don't need every single transaction. You only need your transaction and the hashes in the Merkel path all the way back up to the root, ultimately to the block header. What this allows you to do is you can take your transaction and all the hashes along the way and hash them together and confirm that they're the same all the way back up to the block header. And you can know that your transaction was contained inside of the block in an efficient way that does not require having every transaction or every other Merkel proof. And roughly speaking, so these Merkel path structures scale quite well. If I recall and understand correctly, I believe they scale as log n, because it's like a sort of binary search or something like this. So it's like what that means is, so basically as the volume of transactions on the network grows, the size of the Merkel paths grows exponentially slower than the number of transactions. So roughly speaking, it would be something like, if the number of transactions goes up by a factor of 10, then there's like one more Merkel path that you have to have. Or I think it might be something, if it goes up by a factor of 2, then there's like one more Merkel path you have to have. Something like this. You could look at the math and figure this out. But the point is that it scales very well, and the point is, even at scale with 1 million transactions, the Merkel proofs are still going to be very small. Roughly speaking, the way to think about it is the size of these Merkel proofs are, roughly speaking, the same size as the transaction itself, which is so small that it's irrelevant almost all of the time. So what that means is, okay, so these data structures, so if you have a limited consumer device, it can be your smartphone, and your smartphone is already vastly more powerful than it would need to be able to do any of this stuff. But in any case, you could have a super light wallet, like a card or something like this, that can actually do these data structures, because the amount of computation you need to do is so low that it can be handled by practically nothing by today's standards. So you could have like a card that actually does all this stuff. So, I'm sorry, I forget the name of the company right now working on the card. If I think of it, I'll say the name of it in this video. But there actually is a company working on creating a card doing exactly this. It's Norway. So find Norway, and he's making a company, him and his co-founder, Thomas, are making a company that makes actually cards that does this. Okay, so anyway, What you can do with this is, so here's a missing piece with SPV, and literally, to my knowledge, no one has ever actually implemented this. And certainly they haven't implemented it in a practical way because there are no practical solutions to this yet. When you actually pay someone, so now let's go back, let's do another hand-based demonstration here. Alice wants to pay Bob. So Alice should send a transaction to Bob directly. That's what it means for Alice to pay Bob. Literally just send the transaction directly to Bob. No internet connection required. You can do this in person. Okay, so you can go to a merchant, send them a transaction. Just like you would if I were to draw it with hand motions, what it would look like if you paid in cash, same thing. If you pay with physical cash, you just give them the cash directly. Alice pays Bob. So you can do the exact same thing with Bitcoin. You send the Bitcoin transaction directly, but you should do one more thing. You should also send all Merkel proofs and block headers that you have to the recipient, always. This is another missing piece. So right now we're adding in, as I've mentioned in previous videos, we are working on the peer-to-peer transaction part. We're going to be sending transactions peer-to-peer soon, all based on Paymail, and I'll get to Paymail in a minute here. But we're sending the transactions themselves peer-to-peer. This is just a natural next step where we got to get that going. But we're still not ready for genuine SPV. Genuine SPV is going to require that we send the Merkel proofs of the inputs. So let's think about this for a second. I'm going to do another hand motion here. We have a Bitcoin transaction. So a Bitcoin transaction is a data structure. Again, actually the way I'm drawing it right now kind of looks like a big bill, right? It's like it literally is information that is like cash. You can send it to people. So a transaction actually contains multiple inputs and outputs. So it could be like an input, another input, another input, another input, okay, and then output, and then another output, and then another output. And you can have as many inputs and as many outputs as you want in a Bitcoin transaction. Now the inputs are basically where the signature goes to sign an earlier output from another transaction. So the outputs actually contain Bitcoin in them. It has a certain number of Bitcoin, always expressed in number of Satoshis. So it might have 1,000 Satoshis, or it might have 10 to the 8 Satoshis, which is the equivalent of exactly 1 Bitcoin. Okay? So the outputs actually specify precisely how many Bitcoins you're sending. And the reason why there's multiple outputs is because you can send to more than one person at the same time. Or one person might want multiple outputs. You might want to send, for whatever reason, I could go into reasons which I have to explain in a different video, but there are reasons why one person might want multiple outputs in a single payment. So in any case, it's quite flexible in the sense that you can pay from as many people as you want, or from one person with many outputs, and to one person with many outputs, or to as many people as you want to, as you can with one transaction. So it's a flexible design that has a bunch of wonderful scaling properties that we won't be able to talk about everything in this video, but it's a very thoughtful design that there's a reason why every cryptocurrency either copied it or regressed, because I don't really see a way to improve on this. Ethereum regressed. Again, I'll just have to make that into a different video. But Ethereum actually, the reason why Ethereum doesn't scale is because they didn't understand the thoughtful design of this, and they broke it. Okay, so anyway, so what you want to do is when you're sending transaction peer-to-peer, again, what we want is Alice sends to Bob a transaction, but Alice also needs the Merkel proofs of the inputs and the block headers. So Alice is going to send more data. This other data is not that much bigger than the transaction. So it's like something that you can easily do for free. It's not like it's a burden on Alice to send this around. We just need to build this into standard payment protocols that when you give money, you're also giving all of this other sort of meta information too. So what you want to do is you have a transaction. Alice is going to pay this to Bob. You've got inputs. You've got outputs here. Let's assume right now that the earlier outputs that you're spending are actually confirmed, and that you actually have the Merkel proofs of those. Those are what you're sending. Because if Alice sends all that stuff to Bob, when Bob gets the transaction and the Merkel proofs and block headers, Bob can actually validate that the inputs exist, that you're actually creating a real transaction, and that they're valid and confirmed, okay? Because they're in a block, okay? Now, technically, if Alice gives a new transaction to Bob and Bob is actually offline, so let's consider the offline case briefly. This is extremely interesting. You can actually do fully offline wallets with SPV. Nearly fully. It's like you could connect to the internet once a day or something like this, and that would be adequate for like small merchants. That you could actually have a totally offline store, and when the merchant goes home at the end of the day, they connect to the internet briefly, and they just confirm that all the money was valid, and maybe they got one fake payment, but everything else was valid. Okay, so you can have nearly completely offline wallets using these ideas. Okay, so what Bob does when he receives the money is he simply confirms that the transaction itself is valid in the sense of like actually being structured correctly and actually spending the inputs correctly. He will receive the input transactions themselves, along with Merkel proofs going out to the block headers and the block headers too. So he knows basically it's valid in every way other than he does not know that it hasn't been double spent. But the interesting thing is, if everyone's sending the transactions and the Merkel proofs around, when Bob is in communication with another person, for instance, another person that comes along and pays, and you can imagine that they're all offline. So now Carol comes along and Carol makes a payment. Bob can actually request things like what are the latest block headers and Merkel proofs. And if Carol actually has some of that data, it's trivial for Carol to communicate the one or two of these things that Bob actually wants. So all this can happen for free, or could even cost money, I guess. But it doesn't need to. I mean, it's like we're talking the amount of data is so low that these users can easily communicate this to each other for free. And so long as most people do it, you can have the occasional criminal come along or fraudulent person, and it basically, yes, it will be possible to commit fraud, but it'll be challenging, and you'll find out very quickly. Okay, so even in an offline case. And if you're online, they can't. Because if Bob is actually online, all he has to do is use a new API that does not yet exist to actually ask the miners if the transaction is valid. So Bob will give his transaction directly to the miners when he connects to them and say, is it valid? And the miners will know whether it's valid or not. So he'll have a small amount of trust for the miners, but it's quite low because they're incentivized to do all this stuff correctly. So it's very unlikely that they would violate that. So in any case, so I've just described basically how offline SPV would work, and I hope all this stuff is clear. We will eventually create more graphics and stuff like this, and we won't rely exclusively on hand motions to explain everything. But it takes time to develop this stuff, and it's fairly easy for me to sit up here and explain it in words, and so that's why I'm doing it this way right now. At least we have something out there to explain this stuff. And of course, we're not the only company doing this. I mean, look at, I think Brendan Lee is doing an absolutely fantastic job. I think he's the other person that's doing a very good job specifically trying to create educational material. The Bitcoin Association is involved in all this stuff and trying to get out more information too and things like this. But in any case, we're explaining it just so that people understand, what we're talking about, and people also like my videos and stuff like this. So it encourages me to continue creating content. Okay, so anyway, I want to connect this to Paymail and explain why Paymail is relevant here. I made a video about putting Paymail itself fully on chain. I think that's a good long-term vision, that Paymail itself will actually end up relying on Bitcoin. But Paymail as it is right now actually does not rely on Bitcoin at all. Paymail is actually an internet protocol. Paymail relies on internet technologies. It relies on DNS, and it relies on HTTPS. And that's it, and like other stuff like REST API or whatever. And this .well-known file. So it combines some different internet technologies into one coherent protocol. The way to think about Paymail is that it's a naming and query system for all the stuff that happens before things hit the blockchain. And so you need something like this. I mean, imagine when Alice pays Bob. Let's think about what this actually looks like. What Alice wants to see on her smartphone when she's paying Bob is some kind of assurance that she's paying someone accurately. So for one thing, when Alice pays Bob, she wants to see Bob's name in her wallet, Bob's photo, and a green checkbox that says Bob is real. And she doesn't want to be like scammed, because it shouldn't say, oh, there's some other person named Dave show up on her screen. It's like, wait a second, Dave, that's not who I'm paying. It's a wrong photo, it's a wrong name, and there's a red X instead of a green checkbox. Okay, so Alice should see something on her phone that assures her that the payment is happening accurately. Okay, so she can know that she's paying the correct person. And that will include a name. And this is part of why, what we're doing with Paymail is it's a naming system that's literally just the exact same thing as email. Email is already a ubiquitous naming and query system on the internet, and identity system already. We're just adding stuff to it because we can, and making it possible to do Bitcoin stuff with this. So Paymail provides a naming and query system for things that hit off-chain. So let's think about this. What happens when Alice pays Bob directly? Okay, let's consider the internet case first, because it's a slightly more complicated if they're not actually connected. But if they're connected to the internet, Alice can simply use DNS, HTTPS, and so on, and get the payment information from Bob, and then transmit the transaction over the internet. Now we have to use something like this because there has to be a naming system. There has to be, a query system. There has to be a way for Alice to get the payment information and then to actually broadcast the transaction. So there's got to be some type of communication between them that, by the nature of what it is, these transactions have not actually hit the blockchain yet. I mean, they're not on the blockchain. or like we wouldn't need this. This is the naming and communication protocol that happens before things hit the blockchain. That's what we're doing with Paymail. Okay, so you have to have something like this. It's again why I'm like, because not everyone has actually adopted Paymail yet, and so I'm like, please tell me a better way to do this. If we find a better way to do it, we'll switch. But I think it remains to be seen whether there's anything better than this. You have to have something like this. We're using standard basic internet technologies. I don't think there's anything better. Eventually, it can be fully on-chain when the entire protocol itself and the entire internet itself moves on-chain. But that's far away in the future, and there's no urgency here. We're just going to rely on internet technologies. Okay, so anyway, Paymail provides a naming system. It's going to be bob@wallet.com or something like this, or it's wallet@bob.com or whatever. And Alice will see, something like a name, photo, and green checkbox. The green checkbox is something that we'll just have to talk about in a different video. But I think we do need an opt-in KYC system of some sort so that people can basically choose to prove that they have a real-world identity because most people are actually going to want that. I think most senders and recipients of money are actually going to want to authenticate their real identity because they're not trying to hide anything, and they want to know that the people that they're dealing with are real, and that if they have a legal dispute, they know what the entity is that they have a dispute with, and they can actually use the law as a tool to resolve the dispute. So I think people are going to want to use their real-world identities. They are going to want to keep it private in the sense that they don't necessarily want everyone outside of the transaction to know their real-world identities, but they probably are going to want to know the identity of the counterparty of the transaction. So I think having a green checkbox with a KYC protocol that can be described in a future video or something like this, I mean, there's a lot of work to go into making something like this, but it is possible, and we can add that into Paymail. Okay, so I now want to explain briefly some properties about why Paymail is very natural for doing these things. I mean, the way the internet works right now is based on something called IPv4. Normally we just call it TCP/IP, but because there's this new protocol that has been created, I think decades ago at this point, that's still being rolled out on the internet called IPv6, we refer to sort of the legacy IP protocol as being IPv4. IPv4 does not actually have enough address space for everyone in the world, much less everybody's devices. So you can't actually have a unique IP address on the internet. So unfortunately, the way the internet works right now is, if you are someone that's connecting to the internet, you connect through a router that then connects to the internet. And what the router does is, unfortunately, it messes up your IP address. So when you try to send something outside of the world, your router takes your packet that you're sending, the destination address, and the receiving address is your local area network IP address. It then messes that up and changes it to whatever the internet IP address is of the router and sends the packet outwards. So the way the internet works right now is based on lying. Everyone inside of NAT, so NAT stands for Network Address Translation, which is a very polite way of saying everybody's lying about what their actual IP address is. So your actual IP address of your computer is on your local area network. It is not exposed to the internet. And your router lies to the world about who is really sending the transaction, which is the router isn't sending it, it's you, and you're behind the router. What this means is it makes it very difficult to establish peer-to-peer connections on the internet because you're behind NAT. So when someone tries to connect to you, they can connect to your router because they know the IP address of your router, but they don't know your IP address because it's hidden behind the router. So there's no way for them to just send information into you because they don't already know what your internal IP address is. And the way that NAT works is basically that when you establish a connection to the outside, so Alice connects outside, your router actually has like a processor and stuff that keeps track of this stuff so that something outgoing can correspond to something incoming again. So that when something responds to your outgoing message, the router then does network address translation again on the incoming message and sends it back to you. The problem with this approach is that in order for someone to communicate outside of the network, they have to send a message first, okay? So there's no way to simply receive an unsolicited message from the internet on your device. You can only send something out and then receive something back in again. So you must solicit every message that you choose to receive, basically. Okay, that's the property of network address translation. This creates giant problems for peer-to-peer networks because you can't just publish your IP address and start accepting IP connections. What you have to do instead is you got to somehow connect to someone that actually has a real IP address. And there are all these fancy techniques for working around this. So there's something called a hole punching, which is basically a fancy way involving third-party computers of working around NAT, network address translation. So all this being said, what the point is that basically the way I imagine this working is This just is how the internet works right now. And the best we can do right now is DNS email addresses and HTTPS. And this will de facto rely on third-party services to host stuff. There is no other practical way to do this right now on the internet. It just won't work. We just don't have a genuinely peer-to-peer internet right now. We need to move to a model with IPv6. Once we move to a model with IPv6, then everything's different and you can have genuinely peer-to-peer messages, okay? That you can just send an unsolicited message directly to the recipient. And the unsolicited one would be something like, please give me your payment information, right? So like you actually want to be able to send something out of the blue to someone that the end user actually establishes the first connection to a merchant and not vice versa. Or rather I should say, well, yeah, I guess that's how it would work, but yeah. Okay, so anyway, now let's consider the naming system. So when you understand what I'm saying here, like basically this is just the only practical way to make all this stuff work. It has to be this way. We're just using internet technologies. This is how the internet works. We're just using DNS. Email addresses allow you to like basically have a naming system for a particular domain that's consistent with email. And then HTTPS is just, again, this is just basically standard internet technology that's secure. And it works right now. And we don't have to wait 10 or 20 years for everything to be on chain or something like this. So they're just practical internet technologies. So the way I think this will work is people will de facto rely on third-party services for semi-trusted services such as hosting your public key. And so that's how MoneyButton works right now. We're doing it exactly the way that I think is simply the most practical way that actually works right now, and we actually get it done. And so there's a third party involved, which is MoneyButton, but it's quite untrusted. And I believe that basically every other wallet is going to do it the same way, even if they would rather do it differently, and even I would rather do it differently. But they'll realize that there is no other practical way to do it right now, that you must do it this way, or you're just not going to get it done. I mean, the only other way to do it is IPv6, and that just isn't reality right now. So given the way the internet works right now, the only way you're going to have a naming system and a photo system and a green checkbox when you make a payment is if we're doing something like this using DNS, using email addresses or something similar, and I think everything similar would just be worse because it would just make it inconsistent with existing names that people are using. And you're going to use HTTPS, and that's how it's going to be. And this is all the stuff that happens before it hits the blockchain. Okay, you got to have these naming and query systems working before it hits the blockchain because that's the nature of what it is. You haven't hit the blockchain yet. You're literally, how do you send the transaction to someone? Well, I mean, you got to send the transaction before it can be sent to miners, before it can be on the blockchain, before you can have stuff on chain. So it's literally the protocols that are pre-Bitcoin. It's the stuff that you have to have when you're communicating with someone to send money to them or to receive money before things are on chain. And so we're just using the internet for that. Okay, so maybe I can conclude by just summarizing how all this stuff works in a very, very brief nutshell. The vision here is, actually, let me finish one more thing. I didn't explain how I think we're going to have offline Paymail. Offline Paymail is possible in a nutshell by having something like the way that internet browsers work with having a PKI infrastructure that allows you to have a hierarchy of keys going all the way back to the root authority. We can do the same thing with Paymail. So we can do the same thing with things like DNS keys, going to Paymail, signing stuff, and then your wallet will actually have a hierarchy of actually trusted authorities that are like key signing authorities that can sign off on someone's Paymail. And so you can have a record of that inside of your offline device, exactly like a web browser. Okay, so we can copy the exact same idea and do it that way. You can put this stuff on chain for it to be authenticated, but it'll work off chain. So you can do Paymail off chain. There's going to be a lot of work to make something like this actually work. Sorry, you can do Paymail offline. There's a lot of work to make something like this work, but it is theoretically possible. And so insofar as the offline use case is important to people, basically, we build that in along with other priorities. Like the fantasy vision for MoneyButton would be it's an SPV wallet that also works offline. And so converting that from something, from a purely internet-based thing right now to something that works offline, there's going to be a lot of work here, but it is theoretically possible. Okay, so anyway, in a nutshell, I want to conclude with explaining the overall architecture here. So the point that I'm describing all this, Alice pays Bob. They both have a Paymail. When Alice wants to pay Bob, before she pays him, she confirms on her device, here's Bob's name, bob@wallet.com. Here's Bob's photo. It looks like Bob. Here's a green checkbox saying there's some type of authority that has signed off on Bob's identity. So I know I'm paying a real person. And it doesn't look like Dave, some other guy standing right there trying to scam me. It looks like the right person, obviously. So Alice can then pay Bob. The transactions are sent peer-to-peer along with Merkel proofs and block headers. Okay, so Alice is not just sending the payment itself, but basically the proof that as much proof as she can that it's a valid transaction. Okay, because it's trivial extra information that needs to be added into this stuff. Bob can then validate this stuff, and if Bob's online, everything actually works with a bit of trust, just like it would be with real cash. But if Bob is online, Bob can easily send that transaction directly to a miner and say, is this valid? And the miner will say yes, if it's valid. And so all this can happen instantly. We're not waiting for any confirmations, okay? It's instant payments. It's literally as fast as it gets because it's Alice sends money to Bob. It's faster than lightning because there isn't a bunch of back and forth stuff. It's Alice sends money to Bob. It's like basically as fast as you could possibly imagine. It doesn't get faster than this. You're sending cash at the speed of light, okay? So it's instant digital cash transactions using these technologies. And the relevance of Paymail here is Paymail is the naming and query system that is used before things hit the blockchain, because you have to have something like this. We just aren't using Bitcoin as the internet right now. We use the internet as the internet, and we're using internet technologies for names and queries for all the stuff that happens before things are on chain. And that's what these technologies are for. Okay, that's all I have to say in this video. Thank you for watching, and I'm listening to all the feedback to this seriously. We plan to continue to create more information about everything, and basically if you create a comment on YouTube or a comment in our Telegram channel about these videos, I take everything seriously, and basically, you can help us decide what to create videos about. I already have my own ideas in mind, but I take all input seriously, and basically when someone asks a new question I didn't think of or something like this, I can explain things to people. And yes, we'll be creating graphics, and we won't be relying on hand motions exclusively. We'll have illustrations too, but all that stuff will take time. All right, that's all I have to say for today, so thank you for listening.